Hi, everyone. It's so inspiring to be here. Being in a room full of talented women from this industry truly fills up my heart. So I know it's been a packed 2 days, but let's keep the energy up and dive right in. What if I told you that the very tools we rely on to secure our cloud environments expose us to new risks? Today, we'll explore how attackers can abuse policy as code engines and IAC tools and what you can do about it. Hi, I'm Shelly. I'm a senior cloud security researcher at Tenable. I have 7 years of experience in cybersecurity. I've conducted threat hunting, malware analysis, detection engineering, and more. And a little bit about me, I love cuddling with my cute cats and cooking vegan food. I've been vegan for the past 8 years and still going strong. We'll start with an introduction to the IAC world, then dive into my research process and the malicious techniques. We'll then look at my analysis of thousands of Terraform modules and wrap up with some conclusions. Infrastructure as code, or IAC, is the de facto method for provisioning and managing infrastructure at scale. But policy as code is a less familiar concept. Policy as code is the use of code to define rules and conditions. You need some kind of programming language to write the policies and a policy engine to run them. And one common use case for policy as code is for governing IAC. Usually, you host your IAC in some kind of version control system, such as GitHub. Then, when you update your code, it undergoes a series of tests. Among them, your security and compliance policies run by your policy engine. Finally, if all the tests pass, your code deploys resources in the cloud. This made me think, if an attacker gains access to the supply chain of your policies, what can they do with it to compromise your cloud environment? OPA is the go-to open source policy engine. It is general purpose. You can grant it any kind of JSON input and get back a policy decision. It is commonly used for authorization in cloud-native applications and admission control in Kubernetes. Your application may query OPA to check whether a user is allowed to perform a certain operation, or whether inbound traffic is allowed via a certain port. Then, OPA performs the policy evaluation, which your application is responsible to enforce its decision. In OPA, you use Rego to write the policies. Rego is a high-level declarative language, and we're about to learn you can use it to do some pretty bad things. You may have heard of Terraform, so just to be on the same page. Terraform is the most common IAC tool. It is commonly used by organizations. And Terraform used to be open source, and now it is source available. Terraform is cloud agnostic, so you can use it with any cloud or SaaS provider that exposes API. In Terraform, you write your configurations in Hashicorp configuration language, or HCL, which is also a high-level declarative language. In HCL, you have blocks of different types, as you can see here, and each block has its type and some labels. Also, the block contains arguments and potentially other nested blocks inside it. Terraform has two main components, modules and providers. You can think of modules in Terraform like Python modules. They encapsulate sets of configurations into reusable units, and they can be shared. They are the main way to reuse configurations of resources in Terraform. And when you use a module, you need to use a module block to define the source of the module and the required arguments. The public Terraform registry hosts a lot of publicly available modules that you can use, and Terraform can automatically fetch them during your execution. Providers are the main interface between Terraform and the remote cloud or SaaS providers. There are compiled binaries written in Go. And when you use a provider, you need to use the required providers block in your configuration. Basically, providers can externalize resources and potentially data sources to be used by Terraform configurations. And without providers, Terraform could not configure any kind of resource. Again, the Terraform registry is the main source for public providers. So in this example, you see the AWS provider to configure AWS resources. The core Terraform workflow consists of 3 main stages: init, plan, and apply. Init is where you install your dependencies locally, including the required providers and modules. Plan is where you create a diff between the state in your code and the current state in the cloud. And apply is where changes are taking place. Keep these stages in mind, as we will soon see why they are important. Let's dive right into the malicious techniques, starting with OPA. Let's say you have an OPA server, and it's configured to fetch policies from an S3 bucket, and a web application that uses OPA for authorization. In our attack scenario, the attacker gains access through a compromised IAM user, and the only required access here is write access to the bucket holding the policies. The attacker uploads a malicious policy to the bucket, and OPA fetches the updated policies. The next time the web application triggers an authorization request to OPA, OPA performs the policy evaluation, and that's where bad things happen, because this time the malicious policy runs as well, and it may leak cloud credentials to an attacker-controlled server. When I started researching OPA, I dove into the documentation, and I found these built-in functions. They handle basic tasks, like manipulating strings and numbers, as well as more advanced tasks, like signing requests to AWS. And I found this interesting for my research. So, how many are there? Well, quite a lot. So, I looked up some previous research, and I was quite surprised by the lack of awareness around this topic. I could only find a single blog post talking about the malicious use of Rego. And in his blog post, Liam Galvin discussed 2 specific risky built-in functions, the OPA runtime function and the HTTP send function. Using the OPA runtime function, you can extract environment variables, and these may include cloud credentials. Using the HTTP send function, you can send an HTTP request. And he demonstrated how you can leak the whole Terraform configuration that's passed as input to OPA, or the environment variables that you extract using the OPA runtime function, to an external server. And OPA is exposed to this risk mainly if you use policies from third parties, and then a malicious third party can inject such policy to your server. OPA has the capabilities feature, which allows you to restrict the use of certain built-in functions and fail policies that use them. And it's important to note that in the default configuration, all functions are allowed. But the OPA runtime function and the HTTP send function got some bad attention. And I believe if an organization has some kind of security awareness around OPA, these are the functions it would block. So this sparked my curiosity. If an organization prevents the use of the OPA runtime function, can I find another way to extract cloud credentials? Then I thought, OPA commonly runs on an EC2 machine, and it may have a role attached to it. So maybe I can contact the IMDS, or the metadata service, and extract the credentials of this role and leak them to my external server. The IMDS is a term that any cloud practitioner should know. Basically, the metadata service is an endpoint that cloud instances can access in order to query information about themselves or their environment. So I wrote the Rego code to do that. And I basically translated the bash version from the AWS documentation, reaching the IMDS, or specifically IMDS v2, which is the newer and more secure version, and translated it to Rego. So I used sequential HTTP send requests to access the metadata service, and finally leak the creds to my external server. And as you can imagine, policies should not reach other internal servers. This is actually very dangerous, especially if you use policies from third parties. So I ran this Rego code, and success! I was able to leak credentials from the IMDS to my external server. And I did that without using the OPA runtime function. Let's see a demo. Our OPA server is configured to fetch policies from an S3 bucket. And our attacker listens on HTTP. The attacker writes the Rego code we just saw to contact the IMDS and leak the credentials to his external server. Finally, he uploads this malicious policy to the S3 bucket holding the policies. And the next time the web application triggers a request to OPA, policy evaluation takes place. And that's where the malicious policy runs and creds are being exfiltrated to the attacker-controlled server. Then I thought, what if an organization prevents the use of the HTTP send function? Can we find another way to leak things, credentials, or other data outside of the environment? The net category caught my eye. Sounds like networking. So I dove into the documentation again and looked through all the different built-in functions. And one specific function caught my attention, the net lookup IP address function. It gets a domain name to resolve and returns an IP address. So I thought, what if I look up a domain under the attacker's control and monitor the DNS requests? So again, I wrote the Rego code to do that. And this time, I concatenated an access key that was hard-coded in the Terraform configuration that OPA got as input, as a subdomain of my malicious domain. I passed this string to the net lookup IP address function and monitored the DNS requests on the attacker's side. I ran this malicious policy, and success! I was able to leak data outside of OPA using DNS tunneling. I did that without using the HTTP send function that's commonly restricted by many organizations. So up until this point, we've talked about OPA, which is a policy engine. Now let's talk about Terraform, an IAC tool. I wanted to see whether such techniques can be applied to Terraform as well, since it also uses a high-level declarative language, HCL. Terraform has data sources, which allow you to fetch external data to be used throughout your configuration. And one cool thing I found is that data sources execute at plan time. Recall the 3 stages we talked about earlier: init, plan, and apply. You may think that the plan stage is read-only, but actually, code gets executed during this stage. So an attacker could use existing data sources, for example, the HTTP data source, in order to leak data to his external server. Or the external data source, in order to run custom code on the machine running Terraform. And Hashicorp states in their documentation that the external data source is only an escape hatch for exceptional situations. So, for example, an attacker could write a custom Python script to extract credentials or other environment variables using the env command and exfiltrate the results to his external server. Terraform also has provisioners, which allow you to run code on the machine running Terraform or on the newly provisioned infrastructure. And again, Hashicorp states that provisioners are only a last resort. So you could use the local exec provisioner to, for example, run curl to fetch an external payload, grant it execution privileges, and finally execute it on the machine running Terraform. Or you could use the remote exec provisioner to run code on the newly provisioned infrastructure. So, for example, you could run a coin miner on an EC2 machine you just created. Then I thought, why not try my DNS tunneling technique in Terraform as well? So I found this DNS data source. And again, it allows you to look up a host and get back an IP address. So I concatenated a local string from my configuration as a subdomain of my malicious domain. Again, I monitored the DNS requests and ran this HCL code. And success! I was able to leak data outside of Terraform as well using DNS tunneling. What about extracting credentials from the IMDS? I wrote the HCL code to do that, and I used the HTTP data source in order to contact the metadata service and finally leak the credentials outside of the environment. But this time, I got an error, because the HTTP data source does not support the put requests. It only supports get, head, and post. So this is yet another reason to use IMDS v2, the more secure version that requires the use of the put method. So now that we know the various ways attackers can abuse Terraform, let's look into the easiest entry point, third-party code. I wanted to see whether such third-party code has already been published to the public Terraform registry. So I defined all the risks we've just talked about using Python and scanned all the modules in the registry against them. I calculated the percentage of modules that each block type appears in. And this is what I found. The DNS data source and the external data source are the least prevalent. They rarely appear in Terraform configurations. So if you bump into one of these in your organization, it's an artifact worth looking into. And to avoid creating alert fatigue, I suggest you start by detecting these anomalous blocks first. We now detect these in Tenable Cloud Security. One specifically interesting module got detected during my analysis. It had a weird-looking domain and sensitive HCL parameters inside the requests. And I found out this was another researcher's POC, demonstrating how you can leak data outside of Terraform. And look, it looks completely legit in the Terraform registry. It was even assigned the AWS logo only because it uses the AWS provider. And it had almost 3,000 downloads, which is a fair amount of downloads for a POC. So I wondered whether these are all scanners and researchers like me, or actual victims that fell into this trap and downloaded the module. Let's see what some popular scanners have to say about our malicious configurations. You might be surprised, but the most common scanners almost always fail to detect the risks we've just talked about. I used Chekhov, Trivi, and Kix in my analysis, and the results were disappointing. The industry is behind. In this example, one vendor suggests that you leak secrets over HTTPS instead of HTTP. And I won't mention the vendor's name, but that's actually a very dangerous recommendation. This area is so underexplored that even security vendors that scan IAC get it wrong. Another vendor suggests that you remove this potential exfiltration HTTP request while highlighting an SSM parameter block, which has nothing to do with HTTP. I really wish security vendors would step up their IAC security game. Before moving on to the mitigations, I quickly want to talk about a CVE I found during my OPA research. I looked into the various inputs that OPA accepts, and I found that I can pass a UNC path as a Rego rule parameter. And this means when OPA runs on Windows, I can pass a remote share controlled by an attacker. And during the SMB authentication process, the NTLM credentials of the logged-in user are passed to that external attacker server. That's where the attacker can catch the credentials to relay the authentication or crack the password. For anyone who wants to dive into the details, we now have a blog post up with all the details in depth. I want to give a huge shout out to Styra, the maintainers of OPA, which were super cooperative in working on this. And within a few weeks of my initial report, They published the fix, and it is now available in the new release of OPA. Let's talk about some mitigations. Only use Rego policies and Terraform providers and modules from trusted sources. Also, verify their integrity. Both Terraform and OPA have built-in features to do that. Set up granular RBAC with least privilege. Also, set up logging to analyze and monitor the activity. Limit the capabilities and network access of these applications and the underlying machines. And finally, if you remember just one thing, remember this. Scan before you plan. The plan phase is not read-only. Place your scanner before this stage to identify security risks before execution. We're coming to the end of this presentation. I would just like to share with you some key takeaways. Look beyond IAC misconfigurations. Look for code execution and network activity done by non-resource blocks, especially if you use third-party code. Also, I suggest you explore less researched areas, like OPA, for new attack vectors and vulnerabilities. And finally, research open source tools. Many IAC and PAC tools are written in Go, making them easy to read. Also, these commonly have active communities and a responsive security team. Thank you so much for listening. I'll be glad to take any questions, and also feel free to reach out to me on Twitter.